Okay, today we're going to continue our notes on significant figures, how to count significant figures, and operations such as multiplication and division with significant figures. We're going to continue it on page 15. You should already have your rules for significant figures there. Before we start talking about that, let's talk about why we have significant figures. First of all, let's take a look at this meter stick. The numbers along the top edge are centimeters, and the small marks in between are millimeters. I'm going to call them tenths of centimeters. Now suppose I have a measurement that goes to this point right here with the blue arrow. You can see that there's the 7 centimeter mark and the 0.2 centimeters, so 7.2 centimeters, but you can see that the arrow is in between the 7.2 and the 7.3. So the smallest digit that we know is 7.2, and then we're going to estimate the third digit. And since this is very close to 7.2, I'm going to call this 7.21 centimeters. Now, this last digit, the 1, in the hundredths of a centimeter place, it does have some ambiguity. It is a little bit variable depending on who's doing the reading. So just because we don't know it exactly like we do the 7 and the 0.2, does that mean that it shouldn't be counted? And the answer is no, it should be counted. This is a real difference between 7.2 and 7.3. Is there some uncertainty in it? Yes, but it's still significant. We estimate the last digit, and we recognize that there is always going to be some uncertainty in the last digit. Suppose it had been right on the arrow, or right on the line there for 7.2. Does that mean I would write 7.2? And the answer to that is no, because that would imply that the 0.2 is uncertain. And we don't want that. The 0.2 is not uncertain. We need to show that we can read between the lines. So if it had been on that line, we need to show 7.20 to indicate that hundredths place and say that we're measuring with enough detail that we know that hundredths place. Now in your notes, you already have rule 0 written down. It basically says that all non-zero numbers are significant. So 3.89, they're all non-zero, so there are 3 significant figures there. 938.3, there are 4 non-zero numbers, they're all significant, so there are 4 significant figures there. Rule 0 is pretty easy. Now rule number 1 talks about zeros. This 0 right here, 202, the tens place 0 is a sandwich 0 because it's between 2 other non-zero numbers. Anything between 2 non-zero numbers is significant. So since it's significant and the others are significant, there are 3 significant figures here. Here are some other examples. 67000045. All of these zeros in the middle are sandwich zeros, which means they're all significant. So that means we have 8 significant figures in this number. 0.150098. These 2 zeros are sandwich zeros, so we're going to count them, which means that we have 6 significant figures. Now, I didn't talk about this 0 in the front. I'll talk about that in just a minute when we look at rule number 3. Or rule number 2, pardon me. Okay, leading zeros. Leading zeros are never significant. That's probably what you have written down. This includes zeros even when there's a decimal point present. So if they are in the front and there's nothing in front of them other than another 0, they are not significant. It doesn't mean they don't need to be there, but it does mean that they are not significant. Let's take a look at some examples. 0.0098. The 3 zeros in the front are leading zeros, so they are not significant. That leaves only the 2 non-zero numbers at the end. That means we have 2 significant figures. 0.0884. The underlined zeros are leading zeros, so they are not significant, which means we have 3 non-zero numbers here that are, so we have 3 significant figures. Now, just because these 2 zeros and this 1 zero are not significant doesn't mean that they don't need to be there. If I removed those zeros, the first number would be 0.98, and that's a lot different than 0.0098. So they do need to be there. They're placeholders in order to push the significant digits out to the thousandths place and the 10,000ths place, which is where they need to be. Rule 3 covers trailing zeros. The rule that you have written in your book from yesterday probably says something like, trailing zeros are only significant if there is a decimal present. And that means a decimal present anywhere in the number. So 202.00, there's a decimal present here, which means these trailing zeros are significant. The sandwich zero is also significant, which makes all of these digits significant. So there's a total of 5 of them. Let's look at some others. The number 1,000 with a decimal point at the end. There's a decimal present in this number, which means these trailing zeros are significant, which means we have a total of 4 significant figures. 45,000. Notice that there is no decimal present. Of course, we know where it is. We call that an assumed decimal, but we don't see one. It's not explicitly written, which means that these 3 zeros are trailing zeros when there is no decimal present. It means they are not significant. So there are only 2 significant figures in this number. This number, 450.000. These are trailing zeros. There is a decimal present, which means they are all significant, which means there are 6 significant figures. The last number has all 3. We've got some leading zeros here, a sandwich zero, and a trailing zero. Leading zeros are never significant, so we don't need to count them. The first one that is significant that we count is the 4. We count the 5. We count the first 0 because it's a sandwich zero. We count the 5. And then the trailing 0 is counted because there is a decimal present. That means we have 5 significant figures. So 45050. Again, this leading 0 right here, it's not significant, but it has to be here or else we have a completely different number. Here are some additional examples of varying types. In this case, we've got some sandwich zeros, and there are 6 significant figures. In the next example, 9,800, there's no decimal present, so these trailing zeros are not significant, which means we only have 2 significant figures. Here we have 0.009800. We have 4 significant figures. The leading zeros don't count, but the trailing zeros do because there's a decimal present. Let's talk about rule number 4 for just a minute. Rule number 4 only applies when we're doing math with numbers. When we're doing math with numbers, we need to recognize that defined unit conversions have unlimited significant figures. We also need to recognize that counting numbers or items that are actually physically counted also have unlimited significant figures. What that means is that 60 minutes, if we looked at that and said there's only 1 significant figure there, and we said equals 1 hour, that's only 1 significant figure. That means when later on we do some math and have to round, we're going to have to round to 1 significant figure. What we need to recognize is that this number 60 is really 60.00000 forever, and that means it has an unlimited number of significant figures because, of course, if the decimal's present, all those zeros count. The same is true with this 1. It's really 1.0000 hours and so on. The reason for this is because this is not an approximate unit conversion. This is an exact unit conversion. 1 hour is not close to 60 minutes. It's exactly 60 minutes. It's a perfect number. The same is true of something that is actually counted. If I said there's about 20 or 25 people in a room, that's an estimate. But if I count the people as they come in, 1, 2, 3, 4, and I get to 24, then that means there are exactly 24 people, not about 24. There's no uncertainty in my number, so that again is another perfect number. Now when we round, and you've rounded before in math class and maybe some science classes, you're usually given a place value to round to, like round to the nearest tens place, or round to the nearest whole number, or round to the second decimal. And that's well and good in those classes. But in your advanced science classes like chemistry and physics, you won't be given a place value to round to. You'll have to round to a number of significant figures. Now we've already learned how to count them. In this number, we have 5 significant figures. But for mathematical reasons that you'll learn in a later slide, we're going to have to round this to 4 significant figures. So the 4 significant figures start with the first non-zero number. So the 5, the 6, the 3, and the 1 are the first 4 significant figures. So we'll draw a line right here between the 1 and the 2, and we'll chop off the number and report 4 significant figures here. So our answer is 0.5631. Now sometimes we're going to have to round. In this case we have 0.001775, and we want to report 2 significant figures. So the first non-zero number is 1, and the next one is 7. So we'll draw a line right here where the pointer is between the 2 sevens. Now the second 7 is greater than 5, which means we can round up this first 7 to an 8. So we end up with 0.0018. The 2 significant figures, the 1 and the 7, are rounded up to a 1/8. And remember, we have to preserve these zeros here too, the leading zeros. They put the 1 and the 8 in their proper positions. If we don't have the zeros, we have a completely different number. Here we have 8,792 meters, and we're going to round it to 2 significant figures, or 2 significant digits. The first 2 significant digits are 8 and 7, so we could draw a line here. 8 and 7 are what we're going to report. But the third figure is a 9. It's greater than a 5. A 5 or greater causes the next larger number to round up, so this becomes 88. But we don't write 88 because 88 is a lot different than 8,800. These other 2 are replaced by zeros as placeholders. They're there to push the 2 8s out to the thousands and hundreds place, just like they were over here. This was 8,000 and this was 700. They still have to be in the same place value even after they're rounded. It just means that we don't know what these other 2 are. We're counting by hundreds, and anything that rounds to 8,800 is good. So this could be 8,750, or it could be 8,849. These will all round to 8,800. So these 2 numbers here are unknown, but the zeros are placeholders for them. So let's round this to 3 significant figures. 46.352. So we're going to keep the first 3, 46.3, but the 3 is followed by a 5, which means we can round it up to a 4, and we get 46.4. Here's the same number. We're going to round it to 1 significant figure. Well, the 1 significant figure is this 4 in the tens place, otherwise known as 40, but the ones place is more than a 5. A 5 or more will round up, so the 40 is going to round up to 50. Notice there's no decimal point. That would make this 0 significant, and it's not. The only significant number is in the tens place here. Same number to 2 significant figures. The first 2 are 4 and 6, so we'll keep them. The next one is not a 5 or more, so 4 and 6 is the way it will stay. 46. Now that you know how to count significant figures and you know how to round significant figures, what are we going to do with them? Well, the reason we learned how to count them and round them is because when we perform mathematical operations like multiplication and division, we're going to have to round our answer. The problem is when we multiply or divide that our answer is not going to have, or it may have more significant figures than it deserves to have. When we multiply two numbers, one of them has a small number of significant figures and one has a large number of significant figures. We need to round to the smaller number. Let's look at this example. We have 4.56 meters times 1.4 meters. The first number has 3 significant figures and the second number only has 2. The answer that our calculator gives us is 6.384 square meters. It actually goes to the 1/1000th place of a square meter. Well, we didn't have any measurement that even went that far. The second number that we multiplied by only has 2 significant figures, and that's the weakest link. That means we're going to have to round our answer to the first 2 significant figures. Now the third is an 8, which is more than 5, so we're going to round this up to 6.4 meters squared, or square meters. How about this guy? 5 centimeters times 11 centimeters. I'm sure you can do this in your head if you learned your times tables, and we would normally say this is 55, and the units would be centimeters squared, but if these are measurements and not just some abstract math class, the 5 only has 1 significant figure. The 11 has 2, but we are limited by the 1 significant figure that we have in our first number. We need to round 55 to 1 significant figure. That's the tens place. The ones place is a 5 or greater, which means we round it up to 60. So 5 times 11 is 60 if they're measurements. How about this one? 0.00018 centimeters times 19.35 centimeters. The first number only has 2 significant figures. Remember, all these leading zeros are not significant. So we only have 2 significant figures here, and we have 4 significant figures here. So the weakest link is our 2 significant figures. Even though our calculator gives us 4, we're going to have to round it to 2, and we get 0.0035 centimeters squared. Multiplication and division are done the same way when it comes to rounding significant figures. Either one of the numbers that you multiply or divide by, whichever one has the lowest number of significant figures, that's the limit on the number of significant figures in your answer. You're going to have to round them off. Also, when you do multiplication and division, if they're measurements, they have units. So here we have meters, centimeters, centimeters. Notice that all of mine have units. Meters squared, centimeters squared, centimeters squared. You're going to have to do the same thing with yours. Make sure that you show the units. Remember that division, the units are still there as well. So you'll have to handle the units on the division and multiplication the way you would normally do that in a math class. If you were dividing a number that was squared, or pardon me, if you were dividing, say, a variable squared, like a squared divided by a, comes out to be a, right? A to the 1. So good luck on your homework, and if you have any questions, feel free to come in the morning before school. I'm usually there by about 6:45.